All right, so continuing on our discussion with the theory of linear equations, we looked at linear independence and how we could use the concept of linear independence for functions to get a fundamental set. And we learned how the fundamental set spans all possible solutions to the homogeneous nth order linear differential equation. We then moved on to non-homogeneous equations, and we saw that to find the general solution for those, we would take the general solution for the associated homogeneous equation and sum it with a particular solution, which basically tells you that particular solutions differ up to a solution to the associated homogeneous equation. And now we're going to bring this all together, this general theory, to look at initial value problems and boundary value problems. We pay particular close attention to initial value problems, although we will discuss briefly boundary value problems. So what is the initial value problem? For a linear differential equation on an interval I, the nth order initial value problem, so here we're looking at linear, right? Because you can't get more general initial value problems that aren't linear, so here our focus is linear. We want to solve this, okay, non-homogeneous equation, subject to initial conditions that we see here, okay? These initial conditions, these are called initial conditions. We specify at a single point x naught the function and n-1 derivatives, okay? Now the non-homogeneous equation goes up to n derivatives. We only need the first n-1. So for example, acceleration problems which are second order, right? The acceleration is the second derivative of position. You would specify the initial position and the initial velocity. Initial velocity is the first derivative of position. Acceleration is the second derivative. So you would specify the speed and position, and then of course the next natural question that comes up is, well, do we get a solution? And if we do get a solution, is that solution unique? And it turns out if we satisfy some basic principles, make some basic assumptions, we can get a unique solution to the IVP, or initial value problem. So let's look at this theorem. Let a sub n, to a naught, and g of x be continuous, okay? So up here, we're going to assume all of these are continuous on an interval I. And we're going to make sure this isn't 0. That's important for every x in this interval. So it's never 0. If x equals x naught is any point in the interval I, then a solution y of x of the IVP exists on the interval and is unique. Okay? And we're going to prove this theorem because it actually shows you why this works, okay? We're going to take all that knowledge that we used to learn about the theory of linear equations as it pertains to non-homogeneous and homogeneous equations, and we're going to apply it here to see why this theorem works, okay? So let's prove it using all our previous knowledge. All right, so this non-homogeneous equation, we're satisfying this. These are all continuous. We know then, and of course the equation is linear, okay? Then we know that the general solution to the non-homogeneous equation looks like this, where these ci, yi, right, this is the complementary function, and this is the particular solution, okay? Complementary and particular. So we have that general solution, and now let's see if we could satisfy the initial conditions, okay? If we could satisfy the initial conditions, because so we want to solve this subject to these conditions. Well, we impose them. So y x naught, we plug in x naught into our general solution. Okay. So on the so we apply x naught, we plug x naught into the general solution, and we set it equal to y naught. Why do we set y equal to y naught there? Well, that's one condition. We have a second condition, which tells us to take the derivative of y, plug in x naught, that's the left-hand side, and the right-hand side is the other initial condition on the first derivative, okay? So you could think about y naught and y as constants, y sub n minus 1, they're constants, okay? And so we've plugged x naught into the general solution and its derivatives up to n minus 1, okay? And now how many equations do we have? 1, 2, n to the nth, because don't forget there's a 0. Like you could think about it as the 0th derivative there for the function. So you have n minus 1 plus 0, okay, which is so n. Plus the 0th derivative. So a total of n equations. And now what are we solving for? Well, we know that we could satisfy these conditions when we find C's that work, okay? We have the most general solution. We're guaranteed that from the non-homogeneous theorem. And so we're trying to see if we could find constant C such that the initial conditions are satisfied. So we have n equations and n unknowns. The n unknowns are these C's. Okay? We could rewrite this as a matrix equation. Just take that system up here and rewrite it as a matrix equation. You got to move the y particulars to the other side. So that's what's happening there. This is just one column vector. This is a column vector, and this is your matrix. Now, when can we get a unique solution for this? That occurs when the determinant is non-zero. Wait a second. We know that this is a fundamental set. Okay? We have that from the theorem on general solutions for homogeneous equations. So this is the complementary. This was the complementary function, and so we know we have a fundamental set. And what is true of that? What's true is the Wronskian does not equal 0. Okay, and what is the Wronskian? Well, the Wronskian is the determinant of this matrix. And what happens when the determinant of a matrix is non-zero? You're guaranteed a unique solution. Okay? So when the determinant's non-zero, you're guaranteed a unique solution. It's non-singular. Then this system has a unique solution for these C's. We find just one C, one that makes, one C1, one C2, Cn, that will make this work. There's only one set of C's that will make this work, and we have what we just did in that case is fix the parameters. We fixed that n parameter family of C's, and we did so to respect the initial conditions. So we're guaranteed then. We just showed that we found a solution and it's unique. And notice how important it was that the Wronskian is non-zero, that this set of solutions to the associated homogeneous equation were linearly independent. So let's see how we could use this very important theorem. So find all solutions to the initial value problem. So here we have a third order equation. So what do we need? 3 initial conditions. Here's 1, 2, and here's the second derivative. So again, this always goes to n minus 1, so it goes up to 2, the second derivative there. Well, take a look at this, okay? What would work? Y equals 0 clearly would satisfy that differential equation, okay? Just plug in y equals 0, and you get 0 on the left and 0 on the right. Great. And y equals 0 would also satisfy these initial conditions. Okay, so y of x equals 0, the constant solution, y equals 0 is a solution. Okay, this trivial solution is a solution. And by the above theorem, it's the only solution. So we could rest our heads. There's nothing more complicated than this, okay? We found one solution by the above theorem because an does not equal 0. Look at that. An is a sub 3 here is 3 and is not equal to 0. All the other ans, they're continuous, okay? So we satisfied the above, the hypotheses of the above theorem. This is linear, clearly, right? The operator L would look like this. Okay, so it is a linear differential equation. And once we found one solution, we found all of them. It's the only solution. We're guaranteed that this solution must be unique. What about this one here? Okay, x squared y of 0 equals 3. Okay, well, it turns out there are many solutions to this IVP, initial value problem. For any c, this function will satisfy not only the differential equation, but also the initial conditions. Okay, so you might be thinking that contradicts the theorem. It does not, because look, a2 of x is equal to x squared equals 0 at x equals 0. Okay? Now, if we restrict the interval to positive, say, numbers, then we're fine. We would end up with a unique solution. But notice that the initial conditions are imposed at x equals 0. So that just goes to show you that hypotheses and theorems have to be read carefully. Okay? And so this differential equation does not satisfy. It is linear, but it does not satisfy, and the coefficients are continuous, but it does not satisfy this a sub n does not equal 0. And because it didn't satisfy that, we found many solutions, so it's, to the IVP. Okay, so just be careful. This does not cause a problem because it doesn't really contradict the theorem.